So this problem is going to be Unit 3, Worksheet 3, question number 3. This is going to be a way in which we will be first using a flipped foo-foo in our heat capacity problems. Previously, we have only ever seen our heat capacity problems solving for energy. This time, we're actually given energy, and we will use that to calculate, in this case, what the final temperature would be. So this question is saying, suppose that during the icy hot lab, that 65 kilojoules of energy were transferred to 450 grams of water at 21 degrees Celsius. What would have been the final temperature of the water? The very first thing we do with this problem, and what we do with every single LOL diagram problem, every single heat capacity, heat of fusion, or heat of vaporization problem, is to draw a heating or cooling curve. So I'm going to start off by drawing a blank curve, and then we're going to read through the question and see what information we can see to see if this is going to be heating or cooling. Suppose that during the icy hot lab, icy hot lab, we should know that that is going to be a heating curve. But if we had never seen the icy hot lab before, we can keep reading through the question and see if there's any other information that can tell us this is heating up. So suppose that during the icy hot lab that 65 kilojoules of energy were transferred to 450 grams of water. Transferred to, that's probably going to tell us that energy transfers into the system. So it should be E plus for our heating curve. So I'm going to say that those two key terms, the fact that it's an icy hot lab and the fact that energy is transferred in, tells us it's heating. Now, we start off at 21 degrees Celsius, and we're trying to get up to some final temperature that we don't know what. What would have been the final temperature? Well, we know that it's probably going to be heating up because this is a heating curve. So I draw that increasing line. At this point, what I'm going to do is I'm going to write down the variables that we see in every single problem, the same variables that we see in our, when we took notes. It's going to be our energy in Q, our mass for M, a change in temperature, and then we need to see if it's going to be our heat capacity, our heat of fusion, or our heat of vaporization. Just going to separate my variables from the values we're going to write down. So what I'm going to do is I'm going to look through the question and try to fill in the information I know. The very first thing is going to be our energy Q. That's going to have the unit of joules, so we're going to write that down if we see joules anywhere. So in this problem, we see, suppose that during the icy hot lab, that 65 kilojoules of energy were transferred. Well, energy, we have our 65 kilojoules. Well, we usually really want this in joules. So we're going to need to go from our 65 kilojoules to some number of joules. What that means is we're going to need to use a conversion factor. Those foo-foos and ladders can really help us set this up. So what we're going to do is we're going to write down on the top of our ladder that we're about to draw. I'm just going to go nice big ladder. So we have our 65 kilojoules. That's what we're starting off with. We can use our conversions of metric units table from when we took notes on foo-foos and ladders to convert from kilojoules, which we're going to put on the bottom so our units cancel out, to joules, what we're trying to get to. Well, joules is actually going to be our base unit. So on that table, the metrics with conversion factors, we can only say our base unit is going to be 1. Then we're going to look on the table to see where those prefixes, like in this case, kilo would be. And then, for our kilojoules, we know that when we have one of our base units, we're going to have 0.001 kilojoules. At that point, we can cancel out our kJs, kilojoules. At this point, we end up with the unit we want to get to, J's. So I'm going to put my 2 lines to say we can multiply across the top. 65, no units, times 1, J for joules. So that's going to be 65 joules on the top, and then our 0.001 no units on the bottom. Now we need to divide the top by the bottom. So 65 joules divided by 0.001 is going to be 65,000 joules. And that's what we can write in our table, 65,000 joules. 65,000 joules is the same amount as 65 kilojoules. We just rewrote it. So that's going to be the first thing in our table. The next thing is going to be our mass. So suppose that during the Icy Hot Lab that 65 kilojoules of energy were transferred to 450 grams. Grams is going to be our unit of mass. So I'm going to write down my 450 grams for my mass. Now, our change in temperature. Well, we know we're starting off at 21 degrees Celsius. So we're starting off down here, 21 degrees Celsius. And then we're going up to some final temperature. I'm doing a capital T for temperature and a lowercase f to say it's our final. That's actually what we're going to be looking for, the final temperature. But because we don't know the temperature we started off at and the temperature we ended up at, I'm just going to say question mark. That's what we're looking for. And this unit should be degrees Celsius. Because we have a temperature change, and this is going to be water, we can actually use our heat capacity for water, C. Which for this one is going to be 4.18 joules of energy are required to change 1 gram of water by 1 degree Celsius. Now we know it's not going to be our HF, heat of fusion, because we don't see the keywords melt or freeze, or something going from a solid to a liquid, liquid to a solid. So I'm just going to cross that off. And then for my heat of vaporization, we don't see the keywords evaporate, vaporize, boil, condense, or the phase change from liquid to gas, gas to liquid. So I'm going to cross that off too. It's just going to be our heat capacity, which is what we use when we see a temperature change. Now, I always like to rewrite our heat capacity two ways. 4.18 joules of energy are required to change 1 gram by 1 degree Celsius. We can also write that as 1 gram changing by 1 degree Celsius requires 4.18 joules of energy. In previous problems, we used the fraction on the left because we were always solving for joules, so joules went on top. However, for this problem, we're actually going to be solving for our change in temperature, degrees C, so we're looking for this unit over here. Now in this case, we want to solve for that as our final answer, and we want the degrees C to be on top, so we're actually going to be using the second fraction this time. So that's actually the fraction we're going to be starting off with. So I'm going to draw my ladder down here. I'm going to start off with that fraction with the unit I want on top. 1 gram times 1 degree Celsius requires 4.18 joules of energy. At this point, I'm going to start off with the top of my ladder, my table, and work my way down with those units. So I know that I have 65,000 joules. Now, I want to get rid of this joule down here on the bottom, so I'm going to be putting that same amount of energy up on top, the unit, and I'm putting out how many we have. 65,000 goes up on top, and we only have one amount of that energy, so my placeholder 1 on the bottom. Now, when I put my unit up on top, that matches the unit on the bottom, they can actually cancel out. So I'm going to cross off both J's. This leaves me with the only units of my problem, grams and degrees Celsius. I don't need grams because I'm looking for the change in temperature. So I'm going to actually write down the next variable, my mass, which is 450 grams. I'm going to write that so it cancels out. In this case, I have my grams up on top, so I'm going to put my grams on the bottom. In this problem, I have 450 grams, and I only have one amount of that sample, so I put my placeholder 1 there. This way, I can, having my grams up on top and bottom, I can cross them out. This just leaves me with my units being degrees Celsius. Because that's what I'm looking for, I can now put my second line in my ladder to say that this all is going to be equal on the left to the right. What I'm going to do is I'm going to multiply everything up on the top now. 1 times 1 degree Celsius times 65,000 times 1. That's going to be 65,000 degrees Celsius. And then on the bottom, I'm going to multiply everything down on the bottom. Our 4.18, no units, times 1, no units, times 450. Once again, no units. That gives us 1,881 on the bottom. But once again, no units. I want to simplify this number down, so I'm going to take my 65,000 degrees Celsius divided by what's on the bottom, 1,881. what that's going to give me is 34.556, I'm just going to round that to 34.6 degrees Celsius. Ooh, and because I know this is a heating curve, I know that that change in temperature, this right here, should be a positive. My change in temperature should be increasing, so it's going to be positive. Now, because I know that this right here is going to be my change in temperature, what I can do is I can use that change in temperature and the temperature I already know to find out what my final answer should be. Well, for this problem, we're starting off with our initial temperature, the temperature at the very beginning, as 21 degrees Celsius. Now, my change in temperature is going to be an increase of 34.6 degrees Celsius. Because I'm increasing by that amount, my final temperature should be a larger number than what I started off at. And by adding it together, the final temperature would be 55.6 degrees Celsius for my final answer.